So this fact about Euler's formula, but it is used all over the place. And one of the consequences is to show that K5 is not a planar graph. So I'll explain what K5 is. So the K5 is a graph where you have 5 vertices. Right? It's a complete graph, the 5 vertices and all edges between them. Okay, so all possible edges you have to take. Okay, so when you try to draw it, you'll find that you'll be crossing edges. Okay, so so this corollary says that there's no way, not just it wasn't just my drawing. There's in fact no way that you can embed it in the plane. Okay, it cannot be. There's no planar, sort of realization of this K5 graph. Okay, so how does one use Euler's formula to prove this? Well, suppose it was planar. Okay, so last time we did proof by induction. Okay, so this is another technique of proofs that I guess you are all familiar with. If you suppose not, right? Suppose it is planar. Suppose K5 is planar. By the way, if you try to draw it, I mean, maybe, you said that, why didn't you try to draw it without crossing? So let's try to do that. If you take these guys, so far it's embedded. Okay, so then I cross this way. So instead, if I go around, okay, right, so that's fine. Oh, by the way, I missed one edge here, right? So there was another edge here. So far, so this can be connected to this can be connected to that, right? So far it's embedded, but since it's a complete graph, you have to join all possible pairs of vertices, right? So there's no way to now connect this to that. Okay, and this is what the corollary says. Okay, so there's no matter how clever you try to be, you can't sort of connect up. All right, so without crossing an edge, right? So how does the proof work using Euler's formula? So if you look at the number of vertices, so that's 5. What are the number of edges? Someone quickly. Can someone say what the number of edges are? Yes. Okay. Somebody did it in the chat. It's 10. It's because it's 5C2, right? So you're joining all possible pairs. So therefore, Euler's formula will tell you that the number of regions, okay, I'm just using orange for that, the number of regions, it has to be 7, right? Okay, if there was a planar embedding of K5, has to be 7. But why is this? So we want to get a contradiction, right? So how does that work? So you notice that each region must have more than or at least 3 edges around it. Okay, so the way that complete graph works, you don't have regions that look like this, right? There are no double edges between a pair of vertices, right? Each pair of vertices is a single edge, right? So there's no, so this doesn't happen. So this doesn't happen, and neither does a single edge around the vertex like this. So this also doesn't happen, right? So there's at least, if there is a region, it must have, so these two don't happen, but you must have at least 3 edges, right? So this is sort of the, should have at least 3, okay? But so now if you try to count the number of edges this way, so what happens if you add up? So let me write it here. So if you add up the number of edges around each region, you get, can someone say what you get? So it's, do you get all the edges, or do you get the number of edges, or what do you get? Can someone unmute themselves, perhaps? Anyone? So if I say get the number of edges, so that's wrong, but can you correct it? Yeah, that's right. You get twice the number of edges. That's right. Why? Because if you take a region, right, then an edge that's surrounding it, edge, one of the edges that's around this region, that's in the border of the region, that edge also belongs to a neighboring regions, right? So when you add up all the number of edges, you're counting that edge twice, right? So okay, so you have these two observations. Each region must have at least 3 edges, and then if you add up these, you get twice the number of edges. So that means that twice, so this time 1 and 2 imply that if you look at twice, let me use the color I was using, twice the number of edges, that's greater than equal to 3 times the number of regions, right? So 3 times the number of regions. Okay. So now when you apply it to, so that must be true, right? So if this is planar, this must be true. But then we already computed the number of edges and number of regions. So that was 10 and 7. So if you plug those in, so this would imply that twice 10 is greater than 3 times 7, which is definitely not true. That's the contradiction. Okay, so that's the proof that K5 is not a planar graph. Okay, it's a consequence of, once you know Euler's formula, you can deduce various facts like these, and there are plenty of proofs in graph theory that very nicely use Euler's formula. Okay, so now you might be thinking that, okay, so this is all graph theory. I signed up for a course on topology, right? Where's my, where's topology? Where's the shapes? Where the topology is about, sort of it's the study of shapes in a broad sense, right? So where's the shape? Well, so it turns out that you can think of all this that we were talking about as happening on a sphere, right? So a planar graph, the planar graph is, or it can be thought of as, can be embedded, let me write this, embedded on, let me say, in a sphere. So the basic topological space, somebody mentioned balloons. So this is something that topologists will call a sphere, right? Oops, let me try to draw it again. So I'm also getting used to, I can do it better on a blackboard, I suppose. Okay, sort of blackboard is easier to go sort of one round with a chalk. Okay, so that's my sphere, and you can think of the graphs we were drawing on a plane earlier. You can just imagine them, sort of lying on this sphere as well. Embedded on the sphere, again, embedded means no edges cross. And this time you can see that, so the region, the outside region that we were counting, so we had this, maybe this R1, R2, etc. Let's see, in this case, you just have 3 regions. This outside region is enclosed, is indeed enclosed by, these set of edges right here. So that sort of this graph defines that region on the sphere and so on. So so secretly, what I was talking about earlier, this about planar graphs, is something about actually about graphs on a sphere And what in the Euler's theorem can be thought of as saying, so this is another way of sort of saying, so we say that the Euler number of a sphere is 2, okay? Because if you draw an embedded graph on the sphere, which breaks it up into these regions or these pieces, which are nice, then if you count the number of vertices minus edges plus number of regions, you get 2, right? And the thing where topology starts really is the observation that, let me write it like in, maybe I'll write it in orange, that the Euler's formula, if it's, so Euler's formula is true for any surface that looks like a sphere, that is topologically equivalent. Okay, and this is what one of the notions that we'll have to kind of learn, or you'll learn as we go along in this course. So topologically, let me draw it, and let me write it in red. This is going to be one of these important notions that you'll be learning. Equivalent to a sphere. Okay. What does that mean? Well, if you deform your sphere, so okay, so let me sort of informally say what topological equivalent means. So you can think of topologically equivalent means that you get a surface where you deform your sphere into that surface. So you're allowed to deform by stretching or bending. So stretch and bend, but not tear your surface. You can't make a hole, right? So you can tear or even glue up. Okay, you kind of you identify points. Okay, so that you're not allowed to do. So for example, this particular sphere, so what you could do is you could, maybe you can stretch it somewhere, okay? So maybe you kind of, you sort of deform it, you stretch it, so now it's no longer a round sphere, but topologically it will still be a sphere, right? It's still something that you get by deforming. So maybe if you can deform, you know, stretching these vertices with them, maybe. So sort of vertices and edges, you kind of stretch it so that they kind of, so you can imagine this is made up of, you know, some stretchable material perhaps, or something like that, okay? So, or maybe it's some kind of, you know, sort of a rubber thing. Okay, so, right, so whenever you do this deformation, it's still an embedded graph. You're not changing the number of vertices, number of edges, number of regions, okay? So it is still going to be the Euler number on this topological sphere is still going to be the same, right? It's still going to be 2. Now you can ask, okay, so what happens for a different surface? Let's see what happens for a surface that looks like this. Okay, so oops. So by the way, what is the surface called? It looks like a tire tube or donut or vada or something. Yes, that's right.